This video aims to explain some of the math methods and manipulations that we will be needing for the data interpretation. So we're starting off with the tris and HCl of the reaction. Tris is a white powder and HCl is a 0.1 molar solution. Using the first equation below, we can find the enthalpy of the reaction given the mass and the temperature 0.63 R. I found a diagram from Chem Libre texts depicting 0.63 R. And if you're looking at a temperature over time graph of a reaction during the reaction, you can tell that the 0.63 R relates to a point where the change in temperature sort of flips in its calculation method by integration. Looking at the graph, you can see that it would almost represent a halfway point related to the areas under and above, depending on how you look at it, each curve. So what I believe it is it's actually the halfway point for the total temperature change on either side, making it even overall. So using this temperature 0.63 R, we can split it up into simply an initial temperature and 0.63 of some change in calibration temperature, which can then be simplified to a final minus initial temperature. They note that the subscript I and F represent initial and final temperatures. Now this notes that the first equation is an empirical equation and that the units don't work. Usually this just means that there has been a constant thrown in there that makes it work, and I have the feeling they decided to drop the units in favor of simplicity. You just give it a mass and it will give you joules as an answer. Next up, we're going to look at the heat capacity of the solution calorimeter. So this is under the condition of constant pressure, given that this is simply open to the atmosphere. And we will relate the partial change in the heat term isobarically of the HCl solution and the calorimeter by the partial change in temperature to the constant heat capacity term at constant pressure of the HCl solution and the calorimeter. So what we're going to do is we can rewrite equation 4 by multiplying both sides by dt, and this will give us effectively equation 5 right below it. If we ignore subscripts for a moment, it says that dq is equal to cp times dt. What we can then do is, now that we've simplified it a little bit and separated the differentials, we can assume that the heat capacity at constant pressure is a constant within our small temperature range, so we can then integrate it as a constant, so we only get delta T and Q out of the integrals. After simplifying some of the equations regarding to the materials, now we're going to look at our container. So first, we are assuming that our container is adiabatic. It won't be perfectly, but it should be effectively adiabatic, which means that the heat of the reaction has to equal the heat of our calibration. They have to be the same, but negative. So knowing that the heat of the HCl solution in the calorimeter has to be equal to the lost heat of the calibration reaction, we can substitute in for Q sub P HCl negative Q sub P of reaction, which we can then add straight across to get 0 on the left side and have our Q term end up on the right side of the equation. Moving along, we understand that under constant pressure conditions, the enthalpy change of a reaction is equal to the heat term isobarically. So what this will allow us to do is to substitute in for QP reaction calibration the change in enthalpy of the calibration reaction, which will allow us to basically have another thing that we can know already in our equation. We can also convert the TF minus TI term into the delta T of the calibration for simplicity's sake as well. Moving on yet again, now we're going to look at the heat capacities of the solution in the calorimeter. We know that they are independent of each other because one is the liquid solution, the other is the metal container holding it. So we can assume that the heat capacity at constant pressure of our HCl solution plus the heat capacity at constant pressure of our calorimeter will be equal to the total heat capacity of the two combined. That it would be how much both would absorb in terms of energy to go up in temperature. So this is where the math gets kind of nice, because we can find the change in enthalpy of the calibration run from the empirical equation, we can find the change in temperature of the calibration run through a procedure found in the calculation section of this lab report, and we are given the specific heat capacity at constant pressure of the HCl solution, which was likely just ripped out of a data table somewhere. It is worth it to note that this is the specific heat capacity of the HCl solution when it's 0.1 molar, and the mass of the solution is the total solution's mass plus whatever mass of tris that you're adding. Now that we have three knowns, we can actually solve for the constant pressure heat capacity of the calorimeter. By knowing this, we can then use the same reasoning and logic, yet apply it to the KNO3 and water solution to find the change in the enthalpy of the solution of the KNO3 and water. A quick note that I forgot to add while discussing this is that the constant heat capacity of the water is made from an assumption. We are simply adding the mass of the water in the KNO3 and disregarding any effects that the KNO3 powder may have on the heat capacity of the two combined, because we're just using the constant pressure heat capacity of water in this equation. CP of the calorimeter is going to be the same. That's what we solved for in the equations before. And using these two knowns plus the known temperature of the KNO3 reaction, which is determined through a procedure in the calculations part of this lab report further below, which deals with effectively drawing lines on the graph to find a specific intersection point. Using these three knowns, the heat capacity of the water, heat capacity of the calorimeter, and the change in temperature of the reaction, we can find the change in enthalpy of the KNO3 solution by solving for it. We can then later convert this into a molar quantity by dividing or multiplying by moles as we need, which is the endpoint of this lab.